I'm going to talk briefly about two topics today, and then I'm going to try to focus on a third topic, which is more interesting. This talk's title is Observability and Performance Analysis with BPF. I'm not going to define what observability is, but I'm going to go through it so you can have a little bit more context about the talk. I'm not going to define what performance analysis is, but I'm going to give you some context so you know what this talk is about too. And then we'll focus most of the talk on something called BPF, and I'll try to explain to you what it is. And my hope for this talk is that you actually want to use this tool called BPF, which I think is pretty cool. So let's start with observability. Some people use this definition for observability. It's like your ability to ask arbitrary questions, either they are new or old, and explore where the answers take you. And obviously, the answers will be conditioned to the systems where you ask the questions, and they will they'll be sorry, I just forgot the word. They'll be constrained to the kind of data that you have to actually answer those questions. One of the reasons why people use observability is to be able to actually reason about past incidents and prevent future incidents, as like John and Nora talked about in the previous two talks. As I was mentioning, one of the keys of observability is to actually have data, right? You can ask as many questions as you want, but if you don't have any data about the questions that you're asking, you're never going to get any answers whatsoever. The way that people try to fulfill data for answering questions is by introspecting your programs, adding tracing to your programs, adding logging to your programs, adding metrics to your programs. That is going to give you a lot of answers about, that's going to give you a lot of insights about what the system is doing. But the problem with that is that unless you add all that introspection into your programs, you are still constrained to the code you actually are adding to your programs to be able to answer questions later. So if you don't think ahead about which kind of questions you want to answer in the future, you're always going to have this problem where the questions that you're asking your systems might not be, you might not get any answers for them, right? BPF is something that is trying to solve that problem. I'm going to assume that everyone here runs Linux in production. I know many people don't, but BPF is very related to Linux. So how can we get data as much data as we can from any production Linux system, right? And BPF tried to solve this problem by embedding a virtual machine inside the Linux kernel, and then allowing the kernel to run BPF programs based on events that you can predefine. And in this context, we refer to a virtual machine much more in the context of the Java virtual machine, where you write some code and then compile it into an instruction set and then run it into the virtual machine. So what BPF is doing is really compiling some code and putting it into the Linux kernel and allowing the Linux kernel to execute that code when it receives an event. And you can define those kind of events. the primary way to actually write those programs is to write a subset of C code and then compile it into binary instructions with LLVM. This is actually kind of frightening, and we'll talk a little bit about it later. But I'm going to explain how all this works from a user point of view, right? In reality, a BPF program is divided in two. The first part is all this code that you write that's going to be embedded into the Linux kernel. And then the second part is going to be code that runs in user space that is actually going to inject the code into the Linux kernel in real time without you actually having to compile any module or having to restart your system or anything like that. And it's just going to wait for those events in the kernel to happen, and it's going to listen to it, right? And the way that it loads those BPF programs into the kernel is through a syscall, and that syscall goes through something called the verifier, which is going to make sure that your program is not trying to do something wrong, or something that's going to affect the kernel, something that's going to make your computer crash or anything like that, right? So it runs a static analysis on your code. It runs some kind of heuristics to make sure, for example, that you don't write infinite loops, or you don't try to access memory that don't exist, and so on, right? So when this verifier actually gives you the okay, it's going to load the code into the kernel, and it's just going to wait there for the events to happen. When one of the events that you define actually happen in the kernel is going to invoke the program, and it's going to give the program the information that the kernel has about that event. And then the BPF program that's running on the kernel can communicate with the other part of the program that runs on a user space, and it can pass data back and forth. So when you have all the data from that event, you can send it to user space and do whatever you want. You can aggregate it, you can store it in a time series, you can do absolutely whatever you want with it, right? That's up to you. But that way, you can actually access everything that happens in the kernel from user space and save it for later if you need to do something about it. And the good news is that today I'm actually here to tell you that you don't actually have to write C to take full advantage of BPF. And it's something that I'm trying to tell everyone, and that's why I'm here. Over the last 4 years or 5 years, the BPF community has worked a lot on providing tools for everyone to actually access BPF without having to write C code as their first experience with BPF. So what I'm going to show you today are a few tools that you can use today or tomorrow on your day-to-day job that are going to allow you to take advantage of BPF without actually having to go through writing C code and learning all the kernel APIs and learning how to use LLVM and all those things. But you can still use BPF to extract all that information that the kernel can provide you to do whatever you want with it. Right? And the first tool that I'm going to show you, it's called BPF trace. You can think about BPF trace as a CLI that allows you to write in a DLS language the definitions of the BPF programs. And in this language, you can specify the events that you want to collect information from, and you can specify what you want to do with that information. And something really fun that I like to do is to inspect what my computer is doing at random times. So this BPF program is going to allow me to do that, and I'm going to explain you what all this means in a second. But BPF trace is just a command line that just takes a random string parses the string as a program, and it's going to inject the BPF code into the kernel. First, we're going to define what are the events that we want to listen to. And the first step is to define which kind of hooks we want to attach in the kernel. And in this case, it's a trace point. Trace points are static hooks in the kernel, and they are predefined in every single version of the Linux kernel. So you're guaranteed that it's going to be there. There are other different kinds of hooks that are more dynamic, but they might change depending on the Linux kernel version. So it's always a better practice to use trace points if you have access to them. So then we're going to specify the subsystem that we want to attach to. So in this case, so every time there's a syscall in the kernel, I'm going to attach this program, and then we're going to define which kind of syscall we want to listen to. And in this case, it's just going to be every time some program executes any other program, I just want to know about it. And then BPF trace gives you these utilities and helpers to do things with the information that the kernel is giving you about the event that is listening to. So we're just going to join is a built-in function that is going to print the arguments for every single program that the Linux kernel in my system is going to see. So I'm going to run through this really quick so you can see it. Actually, I have the commands here, so I don't have to type them all. So now we have the command that I just explained in my terminal. And this is running now. It's saying, like, attaching one probe to the kernel. So this is just waiting for me to do something on my system. Right now, there is no programs running anything that the kernel knows about. Obviously, I have all programs running, but they are not executing other programs at the moment. And something funny I discovered recently about my system is that every time I do ls or anything on my terminal, I actually get all this pile of garbage here. So yeah, this is my awesome bash setup that every time I run anything, it's just dumping a bunch of commands. And we can actually learn a lot about this, right? So, for example, I know that it's running Git because it's trying to identify if I'm in a directory that's a Git repository. So bash can actually print on my prompt the branch that's in, right? So, for example, so in order to print this introduction here, it's running all these commands, right? And it runs LLVM, so it detects my environment in LLVM, it moves things around, it runs random scripts. And actually, I can see all this because all these instructions go through the Linux kernel, and the Linux kernel is just printing them on my screen. Right? The Linux kernel is passing it to the user space program and printing it on the screen. And I wouldn't be able to actually see all these unless I went through all my scripts that I run in my bash profile and like think about every single one, what it does, right? But there are many other interesting programs and use cases for BPF trace. And I'm not going to run through them, but I'm just going to run this. So all these are like the predefined events that I can attach a BPF trace program to. If I'm counting them, well, there are a lot of things. I can attach any BPF program to it. So this can give me like any kind of information about what's happening on my system, right? Which is going to be very interesting if I actually want to dive deep into what's happening on my Linux machine. So one of the interesting cases for BPF is doing performance analysis. So we can observe how a program behaves from the kernel's point of view. So we can define rules in a BPF program and say, like, I want to count how long this program takes, or I want to see all the traces, all the points in all the stacks in a program, and I want to aggregate them for later. You can do all those kind of things with BPF without actually having to change any of your programs. You can just use BPF trace. You can write your own BPF programs using C if you want. But that's going to give you a lot of insights into any kind of production system that you have. And obviously, one of the most interesting tools to do performance analysis is flame graphs. And flame graphs are a visualization tool that is going to allow you to see how long it takes to run some operations on your program, and it's going to order the stacks depending on that timing. And a few years ago, I wrote this blog post about how I found like a ball on Docker while I was working at that company. And when I go back now, it's kind of funny because one of the first things I say in that blog post is that in order to actually profile Docker and generate flame graphs for Docker, you actually have to restart Docker because the profiler is not enabled. So, and if you think about it, if the first thing that you do to actually profile a program is to restart the program, you're going to lose all the information that you actually wanted to collect, and you're going to have to wait until the event that you actually want to profile happens again, which is not going to be very useful. But with BPF trace, we don't actually have to restart any program, or we don't have to actually change your program to actually enable a profiler or add profiler information. We can gather all that from the kernel's point of view. So the first type of BPF flame graphs that I'm going to show you is what they're called on-CPU flame graphs. And these are the most common flame graphs that you can see in all the tutorials and examples. And they're going to show you time that your application spends on specific operations. And you're going to see a visualization where you can actually dive into that timing, and you can see where your application is spending most of the time. So what I'm going to do is I'm going to go again through some Docker operations, and I'm going to profile it with BPF. And we're going to see how we can generate those flame graphs based on all the information that the kernel is actually processing for us. And to do that, I'm going to use another tool that the BPF community built, and it's called BCC. And this is a toolkit that allows you to write BPF programs using a combination of Python and C, or Lua and C, or C++, if you want. But it also provides high-level programs that are already defined to work and do things like performance analysis. And the first one is going to be profile. And this is a script that's in that BCC repository that you can download from GitHub. And what profile does is that it attaches a BPF program to a PID, and it's just going to listen to the perf events that happen in that program, and it's going to collect the stack traces for all those perf events in the program. And this is just going to fold all the traces in a specific format that is going to allow you to generate the flame graphs later. going to copy this here. And this is the same command that I just showed you, but just ready for my terminal. What we're going to do here is I'm going to profile what the Docker daemon is doing, and I'm just going to dump the stack traces that the profiler is collecting into a file. And we'll see the file later. I'm just going to download an image. This is going to take a couple of minutes. So what right now is happening is that the profiler is receiving all the perf events in the Linux kernel that are happening while Docker is running, and it's collecting them on the BPF program in one of the maps that are specialized for collecting stack traces. And when this completes, hopefully soon, the BPF program that's in the kernel and has all the stack traces is going to pass the stack traces to the user space, and it's going to dump it in the file. And that way, I can do whatever I want with them. I can save them for later, and I can store them, or I can generate flame graphs like we're going to do in a second. This is taking longer than 10 minutes ago when I ran this demo backstage. Okay, I think I'm going to pause it because we have enough. So now when I stop my profiler, I can go here, and I see like a bunch of random information that at this point doesn't make any sense whatsoever. But what we can see here, for example, is that we actually get traces from Docker inside Docker that are going through the Linux kernel. So I didn't have to modify Docker to add a profiler or enable anything. The Linux kernel actually knows what's happening into my system right now, right? And if I take this data, I can use this flame graphs script to actually generate a visualization for those stack traces that don't make much sense right now. So we get actually this visualization based on what the Linux kernel knows about the program that I was running in a minute ago, right? And we can see that it's spending a lot of time doing SHA calculations. We can also see that actually it looks like what took longer than anything else was actually canceling Docker. So we can actually dive into this stack trace and see what it was doing. Let me increase the font a little bit so you'll be able to see it even better. So here, this distribution registry is the client for the Docker registry that's actually canceling and reading the stream of data. But we can actually, besides seeing the information in our application, we can go all the way to the Linux kernel, and we can see on top here what's happening inside the kernel. So we can actually combine everything that the Linux kernel knows in our application side, in user space, and also inside the Linux kernel, and dive into all this information. But the fun thing about on-CPU flame graphs is that they actually don't show you all the information that you need to that you actually need to profile an application, because on-CPU flame graphs only show you stack traces about when your application is doing something. But it doesn't show you when your application is waiting for something else to happen. So for example, this flame graph here, it's showing a lot of information about what happened when I cancel Docker, but it's not showing information about how long it took to actually download those layers, or why it was taking so long, or where the program was waiting for. So that's why we have off-CPU flame graphs. So they are going to show you actually the opposite of on-CPU. They're going to show you when your application is waiting for something to actually come back to it. And BCC also provides a similar program, DAM profiler, to generate stack traces for events that are happening while your application is just waiting. And it's completely similar to profile. It's just a BPF program, and you're going to give it a PID, and it's going to follow the traces. So it's very easy to actually correlate both because the arguments are exactly the same. Let me get this. So in the same way that we generated the on-CPU flame graph before, we're going to generate an off-CPU flame graph to see what's happening while I'm trying to download this image from the Docker registry. And I'm going to dump it in another file so we can also see the stack traces that this is generating. So I'm going to run this again. This time I'll be a little faster. But I'm not going to let it run for a long time because we already saw what happened the last time. So here we get a very similar file than we saw earlier with a lot of information about the stack traces that we didn't know before. And again, I can generate a flame graph from that. And you can see that this is very different than this other flame graph, even though it was the same operation. And while this was giving us the information about what's happening while the application is actually doing some operations, this other flame graph is telling us what's happening while the application is just waiting. And we can dive in here, for example, and we can see that Docker is just waiting a lot of, while the Linux kernel is just copying information around. And same again, we can just dive into all these stack traces and see why Docker is just waiting. Right? So at the end of the day, like, if we actually want to measure what our application is doing, we need to combine these two profilers. Otherwise, we're never going to have like exact information about what's going on in our systems. So finally, I hope I gave you a good sense of what you can do with BPF. And I hope you don't feel like writing C is the only entry point to BPF. I hope you can actually feel like you're going to start using this tool because, as I said before, I think it's very cool and it enables so many possibilities for observability and performance analysis and many other things that I didn't have time to talk about, like DDoS mitigations. There are a lot of people doing very cool things with BPF for DDoS mitigation, intrusion detection, and many other areas. There are a few resources that I mentioned, but I want to mention a few other more. Brendan Gregg's blog, it's a big resource. You can find anything about BPF, about flame graphs on his blog. He also maintains the flame graph repository, and you can download it and run it directly. BCC, there are a lot of tools inside the BCC repo that you can use to do many things with BPF. And BPF Trace is a fantastic tool just to have in your computer and play with it. And it also comes with a lot of tools pre-built for you that you can start using right now. A friend of mine and I had this crazy idea of writing a book for really about BPF. It's a work in progress. It will be released hopefully soon when we fix all the typos. And that was it. Thanks for listening.